Thank you ever so much for coming along, because you are going to be guinea pigs tonight to test our new recording system to see how it works. As far as the presentation in the hall is concerned, you shouldn't really notice anything different there, but we may have glitches, so bear with us if we have a few technical problems. Next, we're going to have Len up to talk to us about a news item, and the topic this time is deep water on Mars.
Good evening. Okay, well, deep water on Mars, and a little bit extra after that. You may have seen this news a couple of weeks ago. This is NASA's InSight lander, and it touched down in 2018 and deployed a seismometer that you can see in this drawing. It's the rounded contraption in the foreground. It also hammered a probe several meters into the ground, which measured the temperature gradient and could therefore calculate the heat loss from the planet. It had several experiments on board, which were all about studying Mars' interior. Here's an actual picture of the seismometer taken from the lander. It recorded 4 years of Mars quakes, ending in 2022, after which the dust build-up on its solar panels ended the experiment's life. Analysis of those quakes has revealed bodies of water deep underground, which was unexpected. The technique used has been developed on Earth for finding water and oil deposits underground. The speed of travel of the quakes, with a bit of AI interpretation, I guess, indicates the material that they travel through. As the data built up from over 1,300 quakes, it identified some areas deep underground, 6 to 12 miles deep, with the telltale signature of water. It's thought that the water is infused within the rock, i.e. it's not like underground lakes, it's much like aquifers are on Earth. At this depth, it's basically out of reach to be used to any future Mars explorers. Mars is covered in evidence of past flowing water on its surface. Today the surface is dry and it's hard to find any evidence of water existing on the surface, except as ice at the two poles. Some of the ancient water obviously escaped into space, but now it's confirmed that there is a lot of it deep underground. The probe was only able to find water directly beneath its location, so it's likely that there's substantial amounts of water all around the planet deep underground. Mars and Earth are quite similar, and with 40% of Earth's gravity, it's probably the best candidate for human colonization. This discovery is unlikely to help colonization, but it's more evidence that virtually every body in the solar system seems to include a lot of water. So probably every exoplanet and exomoon throughout the galaxy, and in fact, probably through the whole universe, has plenty of water. Water seems to be essential for life as we know it, so this is positive news for finding life elsewhere. I just added this extra slide as well. We may not find life on Mars, but a much better candidate is likely to be Europa. Europa is the 4th largest Galilean moon orbiting Jupiter. It's still quite large, nearly as big as our moon. What's special about Europa is its surface is made of water ice. It's pretty certain that it has a huge amount of liquid water underneath the ice. In fact, it's been estimated that Europa has twice as much water as the Earth does. Considering it's much smaller, that's quite interesting. It also has a magnetic field of its own, which is believed to be induced by Jupiter's own magnetic field. Now, the only way this can really happen to Europa is if it has a conductive fluid within it, and that's what it's believed to have, and that is salty water. Current analysis has shown that Europa has all the essential chemicals for life to start, and plenty of energy from radiation from Jupiter. It also has a core which is believed to be geologically active, so there could well be black smokers at the bottom of the ocean, a candidate for Earth, for the beginning of life on Earth, so if they're possibly here as well. Hello. In just over a month's time, craft will be launched, the Europa Clipper. It should reach Jupiter's system in 2030, where it conduct many flybys of Europa. The primary purpose of this spacecraft is to look for evidence of life. Now, NASA are more cautious than that. They don't actually spell that out, but anybody that looks at the experiments and what it's doing, it's about finding life. It has 9 ways of analysing Europa and its environment, including a high-resolution camera, thermal imaging, spectrographs, magnetometers, dust analyzers, radar. It will check everything it can without actually landing on the moon, which is beyond its capability. It can even analyze water plumes if, as predicted, they are erupting from the surface. So I do hope to be around in the 2030s, and then we just might learn about the presence of life elsewhere in the solar system. And that's the news.
Thank you. Very good, thank you. Okay, so moving on. So thank you for that, Len. So tonight's topic is the hidden secret of Starlight, and Richard is now going to do his presentation to us on that topic. So over to Richard.
That's good. I'd like to thank Sean for setting this up and his belief that we do need to know something about the history of things, because that's something we're largely forgetting. And I'd also like to thank you for coming along, because this is an unusual topic. It's not space age, but it's really important. It's an interesting story as well, very interesting story. So, to seek the unknowable, the hidden secret of Starlight. What I'm aiming to share with you tonight is the people that were involved in it, what they discovered, and also the bits of humour and the bits of life that cropped up in this, because there's some interesting characters, and it's certainly a fascinating story. So without more ado, let's go on to the next one. Now, the rainbow. Now this is the secret of Starlight in a sense. Now Arthur C. Clarke once said that what we need to do to appreciate the things was to look at them from the viewpoint of not knowing anything about them at all. I mean, we know what it is, we've seen it before hundreds of times, but think about it. What did the ancients think about it? Because what they saw was an arch of colour that went across the sky. That must have been something magical. Now, it's funny, but a lot of faiths, of course, we know that in the Bible, in the Old Testament, it's the sign that God sent to Noah to say that he would not be using a catastrophe like a flood to destroy mankind again. But it's not the only place that this is recorded. For instance, the Greeks, they had a goddess called Iris, and that was the goddess of the rainbow, which is where we get iridescence from. It also, if you want to believe Wagner and his Rhine cycle, that's on the road to Valhalla. That's the march that you go on a soft road into Valhalla. And if you're sufficiently deafened, you don't mind listening to something very, very loud, you can hear the gods going up there in the last part of Das Rheingold. I only found that out a few days ago, but it's pretty deafening. But it is amazing, and you'd think that something like that would be in the ancient world, would be sort of talked about, etc. But it wasn't really. For instance, the Greeks didn't really have an adjective to describe anything that meant colour. For instance, they couldn't say the sky's blue, because they didn't really use the word blue. It was just they didn't have words for colour. And strangely enough, this applies to science as well. There was a medieval scientist, an Arabian character called Al-Hazen, and he was very interested in light. In fact, he was one of the people that showed that that seeing things was not something that the eye sent out to see something, but actually was illuminated so that you could see it through your eyes, because a lot of people thought that actually when you were looking, you were actually sending a beam out to illuminate things. So even he dealt with things like shadows and reflections, but he never touched the subject of colour. And so it was left for a very long time before anybody did. And naturally, as we find out when we're at school, that this guy, Isaac Newton, did that experiment. So in 1672, Sir Isaac Newton bought a prism in a market. I don't know what kind of market it was that sold prisms, but that's unusual. He made a hole in a blind and then shone sunlight into the room, and he found that there was a beam of colours. And he tried a few experiments. He tried to see, by using another prism, if he could make the colours separate up even more. But he realised that wouldn't work, and he actually confirmed it by using a lens to focus the colours back again, and he got white light. So for the first time, they knew where colour came from. The colour actually was nothing to do with the lens or anything. It was actually to do with the fact that white light is composed of all colours. He came up with the Latin word spectrum because nobody did it. I mean, there wasn't a word for this. There was nothing. What do you call it? So he called it spectrum, which comes from spectre, because that was the way he looked at it. So that's a Latin expression. It was quite incredible that this was the first time this had actually got into anybody's consciousness. In fact, some people didn't believe it at all. The great German poet Goethe actually said he hated Isaac Newton because he broke up white light into those colours, and he thought white light should be pure. But of course, as we know, it isn't. So in 1801, William Wollaston performed a similar experiment, but he used a lens, so it actually was more focused. And he noticed a few sort of lines just going through the colours. But he thought that they just marked the colour changes. He didn't really, I mean, what would you really think if you saw it? Because he probably didn't have a very good prism, maybe he didn't have much light to actually see the darkness between the lines, that make up the lines. So actually he did redeem himself, because after it was known what these lines meant, he actually did some work on spectroscopy. He also had another claim to fame. I don't know if anybody remembers William Hart Davies' programmes Local Heroes, which was people, scientists, etc., that he ran around the country looking at. Adam Hart Davies was a publisher and science expert. And he picked up William Wollaston because he invented something that pilots use every day, a heads-up system. He actually developed something that if, say, you were doing a landscape, you were doing a watercolour, you could actually draw by having it projected down onto the paper so that you could actually draw it. So even if you couldn't draw, you could do watercolour painting. Now, the very next year, so William Herschel, of which we know quite a lot, he did an experiment. What he actually did was place a thermometer in each of the colours to see if there was any temperature difference in them. And he was absolutely astonished when the one that was placed outside the red end, where there is no light, actually the temperature shot up. And that was the discovery of infrared radiation. And within a year, a guy in Germany had found ultraviolet. So all of a sudden, the spectrum's expanding a little bit. Oh, that's the wrong thing. There you go. So, the hidden secret of starlight. There's a roadblock. In 1846, Augustus Comte published a treatise on philosophy. It was actually on the philosophy of science. I've looked up through Wikipedia and other things about this philosophy, and actually it is very good. It works in some sciences. It doesn't really explain what it is, and it might be too difficult for me to understand anyway, but it goes on in glowing terms about how it creates order and method and all the rest of the things that there is. But of astronomy, this is his remark: the stars are only accessible to us by a distant visual exploration. This inevitable restriction therefore not only prevents us from speculating about life on these great bodies, but also forbids the superior inorganic speculations relative to their chemical or even their physical natures. Bang! But he was wrong, and the story carries on. In fact, he was... I'll keep doing that. Let's get this, keep it bad. Josef Fraunhofer. Now, he lived in Munich. He had a very impoverished childhood. He was apprenticed to an optician, but the optician wasn't very good to him. He was treated him like any typical apprentice of the day. It was kind of be kicked around and sort of, you didn't learn very much, and you just had to make do what you learned from sort of watching. However, the place fell down. So it obviously wasn't a very good place. Unfortunately, the Elector of Bavaria was doing a progression up the street, and he saw this, and he thought to himself, that lad could maybe do something. So he invested money in him and got him to learn optical work properly, and he became the very best maker of refractors of his time. In fact, the other thing he invented was the German type mount. That's why it's called the German mount. So if I pinpoint that this, got the little thing, there we go. That's the German mount there. How many times have you seen that? It must be common on, in fact, nearly every telescope has a German mount. Not always the best kind of mount actually, but for refractors, it's certainly very good if it's well made. And that telescope there was the one that was used to discover Neptune in Berlin Observatory in 1846. And JWST and Gallet, who were the two people that did that, they used that telescope. It was JWST that actually looked through the scope, and it was Gallet that said that star is not on the map. And that's how they discovered Neptune in I think it was September 1846. But he went on to greater things, and he developed a spectroscope and other bits and pieces, and he actually did a lot of work on spectroscopy itself. He counted and mapped 600 lines on images, but really he didn't know what to do with them. I mean, he just counted them up, and what he did do was he lettered them A, B, C, D, E, F, and so on, which are still used today, believe it or not. So he was right at the forefront, and actually did the first stage of scientific investigation, and that's why we call them Fraunhofer lines to this day. Now we come to Father Angelo Secchi. Now, he actually was a Jesuit priest, which means he was the Society of Jesus, which is their technical name, founded by St. Ignatius Loyola. Most of the Jesuits are actually scientists. In fact, the current person that runs the Vatican Observatory is a Jesuit, so they're still going. But he was a very clever guy. He did an awful lot of stuff. Here he is. He's got this place at Castel Gandolfo, which is over a lake. It's the Pope's summer residence. Now it's a holiday place. You can go there and you can stay there. But I'm told that the sky is very polluted by smog from Rome. But he was one of the first people to photograph a total solar eclipse and realised that the corona was connected to the sun, because up until then, people had thought it might be something to do with the moon. He also discovered 3 comets, and he corrected the catalogue of double stars produced by JWST at the Pulkovo Observatory in Russia. That's a massive volume of 3,500 double stars with their positions, distances, position angles, all carefully noted. So he actually was intelligent and clever enough to be able to correct it. He was the first astronomer to attempt to construct a spectral evolution from his observations. And this here is his little different setup of different types. First type is the Sun, second type is the Sirius type stars, and the third type is the Aldebaran type stars, and the fourth is the Betelgeuse type. And straight away you can see something that is actually quite interesting, that the spectrum on these 3 is relatively empty at the red end. That is because they're so distant that he couldn't actually get a good resolution. The Sun, however, is much better because after all, the Sun is only 3,093 million miles away, so therefore it's on our doorstep, and it's got so much light that you have to filter it down. So you can get very good resolution. However, with stars, it's much more difficult. And the other thing was, he was doing this visually. This is a visual observations. What he saw is what you see there with the coloured background. So these 4 kinds, they actually highlight things that are interesting too. It recognises that stars like Sirius are totally different from stars like the Sun, and that is completely different to the types that we can now call the M stars, which is the Betelgeuse type stars. They have different spectra. So that gives you some idea of the complexity of this and how you can recognise certain types by their spectra, and that's where the analysis and everything comes in. Now we get chemists, Robert Bunsen and Gustav Kirchhoff. And by the way, if you're interested, Bunsen was the Bunsen that invented the Bunsen burner. It's the same guy. Now they began working by, first of all, they're industrial chemists. They were nothing to do with astronomy. Didn't really worry about that at all. They weren't bothered. But what they were interested in was materials, and they noticed that if you put a bit of salt in a gas flame, it turns yellow. Now, I actually did this. I was 10 at the time, and I've been reading all this stuff about astronomy. I'm really interested in a lot of these things that you could do. And my family had just bought a new gas cooker, and it had one of those gas pistols. You remember the gas pistol on the side that you used to ignite the burners? So I put that on, and I got a bit of salt, and I sprinkled it. It does, it goes yellow. I thought, crikey, that's really, really clever. And later on, they went into this more depth with various metals, and by connecting them and making an arc, you get a flame which, when you analysed, it revealed a secret of lines. And that was interesting because it meant black, white, bright lines. That was interesting because it meant that they were different. Each one was different. So the metal used could be identified by the combination of pattern of lines and was unique to every element. Now, they were into engineering, and this is where the tricky bit comes in. They were very interested in engineering, as the purity of metal was of great importance. Also, they discovered the elements rubidium and cesium. They discovered those. They're called rubidium, obviously red colour, and cesium was a bluey green. So that was their major discovery. But then they disappeared from the scene a bit. Why did they do that? Well, you've got to look at what was happening in Germany at that time. In Germany, they had years of being banged around by Napoleon. There'd been so much fighting, and it had covered virtually the whole of Germany, from the various states, from Prussia down to the states near Munich and that area. So they determined that they were going to do something about this. Now, apparently, it was so bad that that the carol "Silent Night." Well, that apparently was written the year that the guns fell silent. Now, I didn't know that until a couple of years ago, and there was I saw a program on carols, the various histories. But that is what it was. But what they were doing, cannons are only useful if they don't explode. If they explode, they kill your army. But if they go out, they hit the other army. And this was the problem. Metal fatigue, because the actual metal wasn't pure enough. And actually they found an interesting thing. They couldn't get rid of these two lines in the yellow. That is the sodium lines. It's in D. They're called the D lines in Fraunhofer's classification, which is still used. Unfortunately, most things are actually tainted by a certain amount of sodium. So the one thing that they had to remove from the metal, copper and iron, etc., they had to get rid of the sodium. So here we've got science for engineering. It's not for astronomy. So really, the main push for finding out the elements tended to be in this kind of situation. So that was their overriding passion. But they also got the three laws of the code of the Fraunhofer lines. And you can see at the top, that is a continuous spectrum, just continuous hot objects such as lamp bulb, filament, something like that. Down here you've got the emission lines, which are the normal type of a spectrum. The reason that on the sun and the stars you see these lines, these dark lines, is because you've got the continuous spectrum of the sun behind, and you've got these. They're not shadows, they're actually cutting the light at particular wavelengths. So that is why you get that dark spectrum. So that was a landmark point, it really was, when they discovered that they've made those discoveries, and it proved that this was suitable. You could work and actually use spectroscopy to do things. Now here we come to our hero. This is Sir William Huggins, 1824, 1910. Now it's really difficult to find out much about him. I've read several books, but most of them are quite. The best one was Colin Ronan's book written in 1964, where he does talk a bit about his history. His family were actually involved with cloth and silk merchants in Tulse Hill. After his father died, he sold the business. Now you'd think, crikey, that's a bit strange thing to do. Well, there's two things. One was he wasn't really interested in running a business. He had a history of being at school and learning a lot about science, and he wanted to do something scientific. But also there's another reason why that happened. Now at the time, that in the 1850s, what was happening was that silk and cotton cotton was being transformed into things in the mills in Lancashire. It wasn't coming from India as made up, and also silk was being made artificially. So people that imported silk were finding their market slowly declining. But it would have given him a lot of money. So in other words, he wasn't running a shop, because they were actually merchants. They're mercers. So you can tell he'd had a fair amount of money. After his father died, he sold the business. In 1856, he bought a 5-inch refractor. Now, a 5-inch refractor is quite a big piece of kit. It's got a lens that's 5 inches across, but it's about 7 or 8 feet long. It has to be held in an observatory. It's a solid piece of equipment. When you talk about 5-inch telescopes now, people imagine something about this sort of size. No, this was pretty big. So it would have cost a lot of money on an equatorial mount. Then he looked around at the sky and looked at things, and he did some work on double stars, etc. But he was looking for something to really get his teeth into. And he happened to attend a soiree at the Pharmaceutical Society in London, hosted by Kirchhoff and Bunsen, who were going around Europe explaining their discoveries. And they came up with talking about spectroscopy, and he realised that this is what he was looking for. And that is exactly what he said. This was news to me like coming upon a spring of water in a dry and dusty land. Here at last presented itself the very order of work for which I, in an indefinite kind of way, was longing. So he bought himself an 8-inch refractor. Now that is even bigger. I have seen one 8-inch refractor in the real many years ago, and it's really big. And also the lens was made by Alvan Clark. Now Alvan Clark and Sons were an optical house in New England, America, and they made many objectives, including the one at the Yerkes Observatory, the 40-inch, which is the largest refractor ever built. Well, there was one bigger than that, but it never worked. It fell apart. That was French. But the 40-inch refractor and the 36-inch refractor at Lick Observatory. So there was one at Lick and one at Yerkes. The 40-inch was at Yerkes, or still is, which is near Chicago. So he'd really gone to town on this. He must have been sure that he could do something. But with that equipment, he was aided by William Miller, who was no mean shake himself. He was a very clever guy and actually worked on some of the things that Kirchhoff and Bunsen were working on. And he kind of led him into doing the work and showing him how to do it and publishing papers with him. So, what did he get? Well, this is such a momentous thing that it really completely changed astronomy. The riddle of the nebulae. On the evening of the 29th of August, I directed the telescope for the first time to a planetary nebula in Draco. Now, I've put in brackets NGC 6543. It's easy to see. It's virtually overhead. It's sort of underneath the plough. It's one of the brightest planetary nebulae. And this is it here, and I think it's the one that we now call the cat's eye. Somebody will doubtless correct me on that one, but I don't think so. And it's a planetary nebula. But then he said, no spectrum as I expected. The riddle of the nebula was solved. The answer which had come to us in the light itself read, not an aggregation of stars, but a luminous gas. That was the first evidence of gas in space. Up until then, there had been this perpetual argument between a distant set of stars, if they could be nebulous. We didn't know, because it was beyond the resolving power of a telescope, and he went backwards and forwards and backwards and forwards. If anybody's ever read the French, or looked at the French of Messier's catalogue, there's three words that almost everybody would be able to understand. Nebulae, sans, got it now? Never mind. Anyway, so they didn't have stars. But this was the first time, the first proof that there were nebulous objects in space. And this is actually before photography. Photography was getting there, but it wasn't quite. The first photographs taken of the Orion Nebula, which are sort of a little bit later than this, they don't really show much. They're kind of, a beginning amateur taking a picture now would be better than the sort of pictures that you've got, even by the very best person in the business that would take pictures of them. So really, that was incredible. it just solved a problem without that people have been, just the doors open. You could now, but he also saw several things that didn't, and that, so in actual fact they were not all gaseous, some of them weren't, but certain of them were, and that over here is the spectrum of this, which he calls it 37H in Draconis, H1V Draconis rather. That was Herschel's designation, which ended up being NGC 6543. But he picked it because it was high up. Now there's a reason for that. When Secchi was observing, he noticed that when doing spectroscopy of stars, that if you were aiming lower down, the spectrum was very slightly different. Now it wasn't different because the star had changed. What caused the problem was water vapour in the atmosphere. So he was the first person to actually see that, and that is why, because he wanted to be absolutely certain of what he was doing, he aimed at something that is virtually on the zenith in the summer sky. So that really was a major turning point. So after his mother died, he'd stopped work for 2 years after his mother died, because he'd looked after her for so long that he didn't know what to do. And it took him a couple of years to get back. But then he married Margaret Montefiore in 1875, and this is her. She was a lot younger than him. She's really, really quite young. She was about 25 years younger than him. But they actually had a very good relationship. They both complemented each other in lots of ways. I mean, their discoveries, they were published jointly. There you go. Included spectra and radial velocities of many stars. Now, radial velocity, you have what they call redshift effect. Now, the redshift that he could measure wasn't very accurate, so a lot of his velocities are wrong. But the point was that he found them. Composition of comets. He found that they had hydrocarbon bands. So there was also solar spectroscopy. And he extended into ultraviolet region using photography. Now, he was the first person to use photography. Actually, he tells the story that he built quite a large observatory. You know how they tell you that always build something bigger than you think you're going to need it. Well, it's the same with observatories as dark rooms. I know, because I've worked in a couple of dark rooms, you don't want to be in a small one because you bump into things. So, but he had, when he started, he had just the eye piece with the spectroscope. Then he had to have a little comparison arc. So he had to have an electric arc generating a spectrum of its own for comparison with what he was seeing. Plus the fact, when he started photography, he then had to install the developing equipment in the darkroom, in the observatory, together with a method of coating the plates, because in those days they were using wet plates. In fact, he was the first person to change over from wet plates to dry plates. So you can imagine it must have been really difficult. You can imagine on a cold winter's night. I mean, I think I'm hard done by looking through a small telescope on a cold night. But that is really, I mean, I've worked in darkrooms that are cold with water and everything else, and it's not much fun. But to actually do delicate measurements and sort of and precise focusing and everything else, and care with positioning the telescope. And the other thing, of course, is the telescope would have to be balanced so that it didn't move, so that its movement was steady. They collaborated with other astronomers working in the field. Now, this is the big thing. All of a sudden, we've got connection, because he connected Angelo Secchi in Rome, Hermann Vogel in Potsdam, and Edward Pickering and Henry Draper in Boston, USA. So all of a sudden, you've got connections. So it was spreading out. People were picking up tips from different things. Also, the one thing that Huggins did that Secchi didn't, Secchi kept looking at stars all the time. He didn't do anything else. He looked at stars. Whereas with Huggins, he actually did much more than that. He looked at comets. He did solar work. He was actually much more into various things, nebulosity, things like that. Now they were a very fun-loving couple by the sound of it, because they used to have parties in their house, and apparently they had a dog. He was a bull mastiff, and the highlight of the dinner party was that William would ask the dog various mathematical questions, and the dog would bark back the answer. And if he got it right, he got a piece of cake. The only thing was that he didn't always get it right, and William excused it by saying, well, he gets fatigued with difficult calculations. So that was that. But he also, the dog, which was called Kepler, he noticed that it didn't like butcher shops. It would never go near a butcher shop. And apparently the dog's family of dogs, its previous generation, were the same. So he asked Darwin his thoughts on this, and it was called anticipated behaviour. In other words, it was inherited behaviour from the previous generation. So he was quite a character, and when he died in 1910, for a few years before that, he'd been working with a major 15-inch telescope, which you can see this is a very big dome. He constructed it himself, apparently, so must have been clever as well. But he was using a 15-inch telescope, and when it finally had to go away, the lens was packed up, and apparently Margaret took him over to the case as they closed the case, and he was quite upset to see that it was finally going, but he'd only lived 2 years longer. But so he was a major force, and also, of course, president for 2 years, 2 runs of 2 years of the Royal Astronomical Society. So he was well connected. Now we move on a little bit here. Puzzle of Saturn's rings. Now we know what they're made of today, because of course we've had flybys, we've had orbiters, we've had all sorts of things. But in the 18th and 19th centuries, people really did wonder about Saturn's rings. In fact, William Herschel, wasn't sure if this what we call a Cassini division, this thing here, if that division was actually not a range of mountains that ran around it at first. He quickly realised he was wrong. But the thing would only be solved if a star would go through and actually go behind Saturn, obviously, and it would be occulted by the rings, but that didn't happen. So there were various sort of thoughts about this, and in the end, a mathematical group posed a competition for somebody to work out what the composition of Saturn's rings was. And the person who took it up was mathematician James Clerk Maxwell. And he proved mathematically that the rings of Saturn must be composed of small orbiting particles, as no solid or liquid ring could be stable. And of course he was right. But you've got to prove that. And although it was later proved by, it was about 1918 before a star actually went behind the rings of Saturn and could be observed, and they actually managed to see that it was transparent. But Professor James Keeler of Allegheny, that's Pittsburgh Observatory, USA, proved that Maxwell's solution was correct. What he did, he put a slit across the major axis of the rings and made a spectroscopic image, and he noticed that you've got these shifts backwards and forwards. So therefore the rings could not be rotating as a solid object. They had to be in what is known as a Kepler orbit. In other words, they're separate. It was an ingenious solution. It just proved it really nicely. If I say easily, not easily, but certainly very well, and it can easily be repeated today. The illustration, by the way, is an illustration that I found in a book I've got it's actually from a similar year to the year that this was done. So this is contemporary with the Saturn and the two characters. So that's what it was thought to look like in the 1850s. That's a drawing of Saturn and its rings. Now, a little story about James Keeler. He later on to work at Lick Observatory, as I've said. Lick Observatory was a strange place. It was like a monastery. High up on Mount Hamilton, it sat there in isolation. There were quite a few men there, nothing else. They had trouble with water, had all sorts of problems with getting on with each other. And there was a guy there, you've probably heard of him, his name was Edward Emerson Barnard. Barnard was an astronomer. He was born just after the Civil War in America ended, and he lived until 1923. He was extremely poor. As a child, he had nothing. His father died. He was brought up by his mother with his younger brother. He had to work at anything to survive. But when he got a bit older, he bootstrapped, sort of got himself going and managed to buy a 5-inch refractor very cheaply from somebody who was virtually giving it away. And he discovered comets with it, and he was very good at it. In fact, when he got married, he had a mortgage on the building, and he actually paid for the house by discovering comets, because there was a bounty that was offered for every comet discovered to the discoverer by some organisation. So you can say that he was obsessed by comets, but he was an obsessive observer. He could not stop. He worked all the time, and up in Lick Observatory, he was exactly the same. He wanted as much time as he could on the 36-inch. He wanted this, he wanted that. But because he was so obsessed about comets and he kept finding them, one of the newspapers contacted Keeler and said, we want to do a little bit of a joke on him, but because he's so obsessed. So he said, can you sort of figure this out? So what James Keeler did, he sent an article to this journalist in which he said that Professor Barnard no longer needs to get up at night to see comets. He has a machine that discovers them for him. It's a telescope connected to a spectroscopic recorder, and when everything passes it by with nothing interfering it, but when the 3 hydrocarbon bands hit onto the selenium cells, then immediately starts bells ringing, and he gets up and goes to find another comet. Well, of course, it was complete tosh. I mean, it was nothing. Of course, Barnard was speechless when he saw it. He was quite cross, but in the end, he was cajoled by the fact that people thought that it was so clever that he must be, it must be using some kind of machine. In fact, well, he wasn't. But somebody did say with a wry smile afterwards that really, did they really think that Barnard would be asleep on a clear night? He wouldn't be asleep. He'd be out there looking for them. So really, the gadget would be useless. Moving on. Henry Draper. Henry Draper was a talented doctor, very clever guy. Also did astrophotography, one of the first astrophotographers. Took first images of the moon and the Orion Nebula, which is one I was talking about, which is really, really small, not very detailed. He and his wife, they didn't have any children. They really devoted on astronomy. I mean, it was something between them. It was kind of a link between them. And they bought their first telescope mirror as a lump of glass to grind down. So this was a real thing with him, but he was also a doctor. And so doing astrophotography, and he did a bit of spectroscopy as well, he actually, he went on a trip, and at the end of that trip he came back, and it was to celebrate his retiring from doctoring and doing his passion full time, which was to do a spectroscopic catalogue of the sky. So he came back from this place. It was very, very cold. It was in the Midwest, and it was in not particularly good weather, and he'd caught a chill. They had this dinner, and he was very, very animated, etc. But no, everybody noticed he didn't eat very much. When everybody gone, he went and had a bath and went to bed. He never got up. 5 days later, he died. His wife was absolutely distraught, and all the dreams had gone. But she determined that his catalogue of spectra should be done. And so she approached these two here, or rather this guy, Edward Pickering. Edward Pickering ran the Harvard College Observatory. Okay, fair enough, very, very good. Sounds good, doesn't it? Harvard College Observatory. Well, actually, it's what the Americans call a dog and pony show, which comes from an old saying of circuses in America, that if you've got a circus that's got a really big name and it doesn't have many attractions, it's a dog and pony show. Instead of being a lion and a giraffe show, it's a dog and pony show. It was run basically by him going around with a begging bowl to all his wealthy friends in Boston, and going around the begging bowl. He found it very difficult to run. What they were actually doing was completing a survey of the night sky from as a catalogue, and he was measuring the magnitudes of the stars, doing it by photography, and also finding variable stars. And he said that he could do this job in this work to create the Henry Draper catalogue in a very short space of a few years, but he would need to be paid for it. And so she set up an account which she paid a huge amount of money each year for him to do it. So Elizabeth, sorry. So this, go back. So this lady here, Wilhelmina Fleming, she started out as his housekeeper, and she had come from England. She got married. She came from Scotland actually, and her husband dumped her when he got to Boston, and he went off chasing gold in California, leaving her pregnant with no means of support. So she became housekeeper to Edward Pickering, and from that he eventually found that she was so good at doing things, and she could not only do that, but he thought she could do the work that was being done in their observatory, which was the measuring of plates to determine magnitudes and positions. And she did. She ran that for umpteen years. But when they were doing I think if I go back a bit, it might be a bit easier. No, it doesn't really. What they did, to undertake the work of the spectroscopy side, they set aside 2 mirror telescopes, 2 refractors rather, with a device up the top that was a lens that covered the entire aperture, a prism that covered the entire aperture. So it produced individual little rainbow star things. In fact, if I go back, you can see this is it here. This was what Annie Jump Cannon, who's the lady over there, that was what she was working on, getting the spectral classes off of that. Very painstaking work. I tell you, this is really painstaking. Now, there's been a lot of complaints over the years about Edward Pickering was using slave labour because he was using ladies. Not true. He got ladies, first of all, because they were more patient, but secondly, they were cheap. But then he was cheap. He was actually underpaid. He worked umpteen hours a day. He was actually head cook and bottle washer there. At times, he even had to clean the toilets. So you get some idea of the conditions this was in. But they worked and worked and worked and worked, and actually produced the catalogue, and also the variable star, and the actual star catalogue. What you see here, it was all on glass plates. There you go. Loads and loads and loads of them. There's the building that they were stored in, a brick building, because they didn't want it destroyed. There's the dome of the major telescope they used, which is that one. and it was connected up to a photographic system to do photography. They also had a station in South America, Chile. There is that Arequipa, and that's actually Annie Jump Cannon. She went down and paid them a visit, and that's her working on the eye end of the telescope. So they could cover both parts of the sky. Now I have a bit of news. It was only in Sky and Telescope last month that this plate stack here, which is priceless, that they've just finished digitising it. It's huge, it's massive, but it's got a huge amount of data on it they daren't throw away, daren't get rid of, because there's things on there they don't know what, you know. So what they did, they worked out what we call a spectral sequence. And they realised that none of the ones really fitted. The trouble was that the prevailing theory at the time was that you looked at an evolution of the stars that either started off when they were really, really hot, and then they got steadily cooler and cooler and cooler, or they were cool and they started getting hotter and hotter and hotter. Now at that time, nobody knew what the power that drove the sun was. There were various ideas, like it was gravitational collapse, it was things falling into the sun. There was numerous ideas, but none of them worked. One of them was that it was made of coal, and the geologist said, you're talking rubbish here. We know the Earth is much older than 4,000 years. So it was wrong. So that's the catalogue that they compiled. You can see how detailed it is. All that had to be written and typeset and everything else. But you see on the side here, there is the spectral sequence that goes down here. And we've got that. The reason that we've got this O, B, A, F, G, KM situation is because they used the same designations for the stars, but just moved them around a bit. They decided that would be the best thing rather than starting A, B, C again with different characteristics. It would be easier to have the tag and put it in the right place. Well, actually it's a temperature gradient. The hottest stars are the O stars, the ones a bit cooler are B, and so on down when you get to G, which is where the sun is. And that enabled the completion of something called the Hertzsprung-Russell diagram, which is this here, where the stars are plotted in absolute magnitude, in other words, how really bright they are, not apparent magnitude, but how bright they really are, and with their spectral type here. And it now means that you can get a plot going up like that, which plots the stars that are on what we call the main sequence. In other words, the ones that are hydrogen burning, and the others are in different positions, so that we know the sun is comfortably here, and they've worked out the sun will go along the Hertzsprung-Russell a bit, and then it will turn off and go into a red giant. So it can be worked out. This is the plot for showing the lives of stars. So what it was that there was the evolution that they were looking for of a star going from hot to cold was completely wrong. But now we can do that because we've got that. We've got the catalogue of stars, the actual types of stars, and you've got a way of plotting them. So that's how we can work out the lives of stars. So that's something. Move on very quickly. Improving resolution. Now, problem with prisms is they're thick. So you lose a bit of light going on the prism. So and also you get unequal bands here. They're not the same width. This was a problem with photographic film that they were using prisms, because it didn't show the red end very well. So you have diffraction grating, and you use diffraction gratings, and this is a modern setup. You have a comparison arc here, light from telescope down here, collimating mirror, make it parallel, down to diffraction grating, red, violet, etc., down to the detector. Just to show you that it works, there's a CD, and you can see the diffraction colours here. Just to show you that the thing actually works. Flagstaff Observatory, Arizona. Vesto Slifer did a study of the spectrograms of spiral nebulae, which they didn't know what they were, in 1910. All of them showed a shift of lines to the red. The fainter ones exhibited a greater shift. He published his results in 1915. This was the first indication that the universe is expanding. Now, it wasn't taken up immediately for two reasons. One, First World War. People like Edwin Hubble, he was in France, who would have worked on it. Secondly, we've been to Flagstaff Observatory. The other observatories don't like Flagstaff very well because they think it was a bit of a namby-pamby kind of establishment, because it was founded by Percival Lowell, who was the guy that believed in canals in Mars. And actually it's only there because he decided to prove it. Anyway, so eventually Edwin Hubble managed to do something with that and prove that that was in fact the case. So there's one discovery straight away that the redshift will show. Now, I'm not going to go any further with the history, because once you get past that point, it gets complicated. It gets really, really complicated. But it's not the complication, it's the fact that all of a sudden people start to stop and think. After that initial burst of discovery, and there were lots of discoveries, the people, the theorists began to get together, and you began to get the birth of atomic physics. And of course, atomic physics, and people like Einstein, etc., and the other people that E equals mc squared, and other people that deal in not quantum mechanics but atomic physics, they worked out that it was actually fusion, nuclear fusion. The sad thing is, of course, as we all know, that ended up with discovering nuclear fusion as well. As we found out at the Second World War, the first was probably not as important as the second one as far as the Earth was concerned, which is really sad. But that was a point at which the old idea of stars being, not having anything to do with atomics, all of a sudden, the very little had to make sense of the pretty large. But we've got some little things here that were discovered. The first white dwarf was actually discovered by Mina Fleming, that's Wilhelmina Fleming, in 1910. There's Sirius, there's the white dwarf down there. And they couldn't find, she was the one who actually found what spectral type the white dwarf was. And everybody said, we don't believe you. And they said, well, there's the proof. You're going to have to find a theory that fits it, which is what eventually happened. Antonia Murray, who worked with the HCO for a while, she discovered that Mizar and Alcor actually have their spectroscopic binaries. Now up until then, nobody had been able to discover them because they're too close to observe. But the point was that now spectroscopy could actually show them by the lines moving backwards and forwards across that they were orbiting each other. That meant that they're the ones that scientists study today, because they're very fast in their orbital motion, so you can get through a lot of orbits very quickly to see how in fact they're moving. It's a bit like in some areas of biology, they use fruit flies if they want to do anything involving generations, because they go through things very, very quickly and you get a family very quickly. It's the same with that. It's just that they do a lot of revolutions. So there's a lot of work tied up with spectroscopy of these very close double stars. The real one that was the puzzle was in 1963. Radio astronomers have had a look and couldn't really understand some radio signals they were getting from various parts of the sky. And then they came across this star. There seemed to be a star that flickered. Now, they couldn't understand this. Variable star observers observed it, but most variable stars, they at least take 3 or 4 days. This was pretty much all the time. When they took a spectrum, nobody could understand what it meant, because there was nothing they recognised. And then Martin Schmidt discovered with Jesse Greenstein in America that they did make sense, but only if you put a terrific redshift on them. So that meant they were tiny little things, they had to be small to flicker, that were at huge distances, at distances of galaxies, for goodness sake. And at that time, people began to wonder, is this cosmological redshift, does it make sense? Does it happen to everything? People surmise that it could be, for instance, something that's been ejected from the galaxy, our galaxy, and was going at a relativistic speed. The guy that did that was Alton Arp. He was a kind of renegade astronomer who persisted in saying that actually that this ball redshift business was wrong, and that he could actually see galaxies that were together were actually discordant in distance measurements. And he produced a catalogue of them, Arp's catalogue of peculiar galaxies. But with improved method of imaging, you began to see that that was not true, and they were not connected. So Arp was unfortunately wrong. I'm not sure on this, but I think that some of you may remember Colin Reeve, but he went over to Burr quite a few years ago now. I'm trying to think who he went with. Can't remember. Anyway, and Horton Arp was a guest there, and he had a chance because he was very keen on something that wasn't, correct. That was his way of thinking. Anyway, so that has now been solved. We know what they are, but it's taken quite a long time to find out they're actually jets of matter from the centres of galaxies caused by the black hole in the centre. And of course, the first exoplanet discovered was discovered by the spectral method. So it's still going strong. It's still working, and as we see, we ain't seen nothing yet. Big debut, Webb telescope, distant past of the universe, using cosmological redshift to uncover the very beginning of time. Well, as far back as we can go. Now, I would be unfair if I didn't actually mention some of the things I got this from. One of them is the Cambridge Concise History of Astronomy, okay. Life and Times of the Telescope, very readable book that is. Planet Saturn, Alexander, 1960. That is a good book. You can't get it now. It's a historical thing of every observation of Saturn that was important. Stars and Their Spectra, very good book on the practicalities and the spectral sequence. Now, The Glass Universe, I recommend anybody to read that. It's the best book I've read, and it can be read like a novel. It talks about all the ladies, it talks about how they did the things, the money problems they had, everything else. It's a very good book, and I recommend it, particularly to any ladies who are thinking of doing astronomy, or even not. It's excellent. It's like a novel. It reads very much like a novel. Life and Times of Edward Emerson Barnard. It's a bit longer. Title is longer than that. It actually goes into the fact that he was, had difficult life and times. That's pretty good. It gives that story in it about the spectroscope on the telescope. Their Majesty's Astronomers Colin Rowland, that's got a lot of stuff in it. And Sky and Telescope, various issues. And also I have the proceedings of the Royal Astronomical Society Journal for the 19th century. So that's how I got bits on Huggins. So that's the end of the talk. I hope you enjoyed it. I hope it didn't get on too long. And I hope it sort of, ticked a few boxes. Thank you very much for listening.